So moisture in the atmosphere, we've got this humidity. Now, how did it get there and how does it get back out? So moisture enters the atmosphere by evaporation, mainly from the ocean, since most of the Earth's surface is covered in water. So that's where most of the evaporation happens from. You're familiar with the water cycle, I'm sure, from past years in science. So evaporation happens from oceans, lakes, rivers, your skin, your pool, puddles in the yard. All those things put water in the air. The other option is transpiration. Transpiration is when plants use water for photosynthesis and then excess water gets pushed out through those stomates in the leaves. That's transpiration. So plants can they actually expend energy to pump water. So they can put a lot of water in a hurry into the air if you're in a very uh, vegetation dense environment, like a rainforest, for instance, or a big field. So factors that affect the evaporation rate are pretty straightforward. When it's hotter, more evaporation happens. So temperature goes up, evaporation goes up, direct. Surface area, how much is exposed for evaporation to happen on. Great example for this one would be a towel. If you go swimming in the summertime and you have a wet towel when you're done, if you don't spread that towel out, if you just leave it wadded up on the deck of your pool or in a bag somewhere and forget about it, that thing will not dry very quickly at all. But if you take the same towel and spread it out so all the surfaces are exposed to the air, it will dry much faster. So the more you spread out the water, the faster evaporation is going to happen. So greater surface area, greater evaporation rate. Moisture content of the air. If the air is already wet, it doesn't need as much water, so there will be less evaporation. My analogy for this one would be a paper towel. The first time you put a paper towel on some spilled water, it soaks it up like crazy because it's dry, so there's room for the water to go in. Now, if you take that same paper towel and squeeze it out, so it's just kind of damp, but there's water in there, it won't soak up the water as quickly or effectively because it's already got some water in it. Air works in a similar fashion. If the air is already near capacity, it's not going to pick up that extra last bit very quickly. So that's an inverse relationship. Wind speed is direct. If you have more wind, you bring in fresh air constantly, more fresh dry air constantly, and that's going to dry up the water more rapidly. So on a breezy day, that towel on the line is going to dry faster than if it's a calm day. Your hair dryer works the same way, or a hand dryer. You blow warm air rapidly across something you want to dry, and it dries it pretty quickly. Now, this one we don't deal with as much, but a large percentage of the world does. If you're near the ocean, the salt content of the water will affect the rate of evaporation. The saltier the water, the slower the evaporation. We, of course, live near the Great Lakes, which are freshwater, so it's not an issue for us. But if you live down on Long Island or near New York City or along the East Coast, West Coast, or any coast of the ocean, this could be a big deal for you. Now, water gets back out of the air through a couple of means. If it's gas to liquid, gas in the air changing back to liquid droplets of rain, that would be condensation. Or if it's going back to a solid, then you have sublimation or deposition, depending on where you look for the answer on that one. But when you skip the liquid phase altogether, usually they'll call it sublimation here in earth science, though the right term is probably deposition. So that's when you get ice crystals, frost, and snow. Either way high up in the summertime, it might be cold enough, or most of the wintertime at any height, you're going to have that. Now, in order for it to happen, for condensation or sublimation to occur, a couple of things have to apply. You have to have the air being full. If the air is not full, it's not going to leak. So air has to be saturated. Temperature and dew point are going to be equal then. And the other thing you need is you need something for the water to stick to. It doesn't like to just start forming ice crystals by itself. It needs a surface to stick to. And that's what condensation nuclei are. Some sort of a surface for water droplets to initially start to form on, and then more can stick to that. Usually in the atmosphere, it's provided by natural aerosols like dust and pollen and things like that. Smoke works, both natural and unnatural. Pollution can also be, particulate pollution can also be something that it sticks to. The average condensation nucleus, we're talking about tens, hundreds, thousands, 10,000ths of a millimeter, so microscopic. The average cloud droplet, if you've ever walked outside when it's foggy and been in that, that's 0.2 millimeters. And the average raindrop's a couple millimeters across, and they can certainly be bigger. So it takes a while to go from sticking to this little bit tiny thing to the average cloud droplet to rain that's heavy enough to fall out. So as condensation or sublimation occurs when air is rising, the air actually is rising fast enough. It can keep the droplets from falling because they're tiny, they're light, and air can be quite a powerful thing. So when it occurs in rising air, tiny water droplets or ice crystals form. They're held up by that rising air. And if you get a big pile of them, all of a sudden you call that a cloud. Clouds are going to form at the altitude where the temperature has dropped to the dew point. You're going to forget this term, but it's called cloud base. The lowest level of the cloud, the height the clouds form at, is called cloud base. That'll be a clue on a crossword puzzle I give you eventually. Most of you won't remember, so we'll see who pays attention here. So evaporation happens, those droplets go up, the temperature reaches the dew point at cloud base. Now all of a sudden you have condensation happening much more rapidly than evaporation, so you have a buildup of water droplets, and the cloud grows and builds. When the droplets get pushed high enough and get big enough, they become heavy, and that's when we get precipitation. So if the condensation rate is high, water droplets or ice crystals join up and stick together. They become heavy enough to fall through the rising air as precipitation. Summertime, those big droplets you get with thunderstorms, they're big droplets because the air was rising really fast inside the cloud. And as a result, they were held up until they were pretty big, heavy enough to fall out of the air. Now, the term atmospheric transparency has to do with how clear the atmosphere is. If you have a whole bunch of aerosols like dust and smoke and pollen in the air, it makes the air less transparent. So as concentration of aerosols in the atmosphere increases, atmospheric transparency decreases. Now, if you have more of the chunks of stuff in the air, that's going to increase your surfaces for water to stick to, and it's going to increase your chance of precipitation. So low transparency air with lots of surfaces for water to form on is going to increase your chance of precip. So atmospheric transparency does not refer to clear skies. It refers to the absence of aerosols. So it's not talking about cloud cover, it's talking about those little surfaces in the air. Now, when you have precipitation happening, it washes those pieces of aerosols, those particulates, out of the air, and it increases the chance of precipitation. So when precipitation rate goes up, atmospheric transparency also goes up because the raindrops and snowflakes literally wash them out of the air, wash the dirt and such out of the air. And that makes it harder for more droplets to form. So you're not going to have it rain indefinitely because eventually you'll run out of condensation nuclei. All right, so we'll stop there.